So after finishing the investment phase of glycolysis, we now are working with two molecules of glyceraldehyde 3-phosphate. And what happens in our payoff phase that we have just entered is we are going to now extract high-energy electron carriers like NADH, as well as generate some ATP to get a small return on our investment so far. And I just want to highlight this because sometimes it is common people forget. We are now working with two molecules because we have, if we look at the number of carbons, we are working with 1, 2, 3 carbons in each one of these glyceraldehyde 3-phosphate molecules. And glucose is a 6-carbon molecule, so we have 2 of these present. So everything that happens from here on out, we're going to be doubling it in our reaction of glycolysis for our total overall reaction. Also to note, I will be abbreviating OPO3 2- as this P with an underline, with a circle around it, just for the sake of simplicity and to try to keep things a little bit cleaner so people can follow more easily. And so in step 6 of glycolysis, we will do our very first oxidation reaction. And the key atom to look at is this carbonyl carbon in our aldehyde of glyceraldehyde 3-phosphate. And if we recall from organic chemistry, the definition of oxidation is any reaction that either decreases the number of carbon-hydrogen bonds and or increases the number of carbon-oxygen bonds. So whenever I think of oxidation, I think of oxygen, carbon-oxygen bonds. If we're increasing it, we are oxidizing something. So that's the way I remember it. And what's going to happen here is this aldehyde carbon, carbonyl carbon, will have both of these happen to it. So first off, what's going to happen is this carbon-hydrogen bond will be broken, so we're decreasing that. And then if we look at the molecule that is formed, which is called 1,3-bisphosphoglycerate, I would call it 1,3-BPG, we will also have an additional carbon-oxygen bond. So I will fully draw this out to illustrate this point. So if we draw out 1,3-BPG, what we will find is that we'll have the same carbon here, and if we look at the OPO3 2- molecule, we have this additional carbon-oxygen bond as well as the rest of the molecule that we had before. And just for clarity, this group right here can also be represented by a P with a circle around it. And so the million-dollar question to ask at this point is, we just broke this carbon-hydrogen bond here. Where does this hydrogen go? And this hydrogen is taken away by NAD+. So we can call NAD+ an oxidizing agent. And by that I mean, by definition, NAD+ is what's causing this oxidation of our aldehyde to occur. So NAD+ comes in, grabs this hydrogen, and it becomes NADH. And the enzyme that is involved in this reaction is aptly named, or appropriately named, glyceraldehyde 3-phosphate dehydrogenase. And the key word here is this dehydrogenase part. And any dehydrogenase enzyme, and every enzyme in the class dehydrogenase will be promoting some kind of oxidation reaction because we are decreasing the number of carbon-hydrogen bonds. Okay, and so just to write this down, the name of this molecule that we have just generated by oxidizing Ga3P is 1,3-bisphosphoglycerate, so 1,3-BPG. And the Gibbs free energy of formation of this reaction is 6.3 kilojoules per mole. And so what this tells us is that if we look at our equilibrium relationship here, we are going to want to, or if we had this reaction occurring in a test tube and you were wondering what the concentrations would be relative to each other, having a positive delta G value is telling us that the left side of the of our equation as written will be favored a lot. So I should probably rewrite my equilibrium curve here just to show that the oops, sorry about the interruption. My OneNote keeps crashing, but I'll do the best I can to keep going. So just to get back to it, what happens here is if we note the positive value of our standard free energy, if I were to correctly draw my equilibrium relationship here between the two sides of this reaction, what we would see is we would have the products be favored a lot more than the reactants. And continuing, the next thing I would like to note is how similar this functional group on 1,3-BPG resembles a carboxylic acid. And what we'll note is that if we were to break this oxygen phosphorus bond, we will be left with a carboxylate, the conjugate base of a carboxylic acid. And what will happen in the next step 7 of glycolysis is we'll have an ADP molecule come in. An ADP will have a terminal oxygen with a negative formal charge. Therefore, that oxygen will be a strong nucleophile. And what you'll note is that this phosphorus here has a partial positive charge, which makes it a pretty nice electrophile. And so the oxygen on ADP will attack and form a bond with this phosphorus, and the two electrons that were once shared between this oxygen and phosphorus will be pushed onto this oxygen, the alpha oxygen, on our carbonyl. And the reason this reaction happens so favorably is, number one, we've got a nice electrophile and a strong nucleophile, but also the resulting conjugate base that we get, as we remember from organic chemistry, has a very nice delocalization of its charge. And by that, I mean the negative charge that will get placed onto this oxygen as a result of this nucleophilic attack can very easily be delocalized between these two oxygens. So these two oxygens will resonate the negative charge, and the resulting conjugate base will be very stable. And so to write out what is happening now in our reaction, 1,3-bisphosphoglycerate now becomes a molecule called 3-phosphoglycerate because it just lost one of its phosphate groups. And this reaction is very unidirectional because of the things we just discussed. And the resulting molecule looks like this. So we'll have the same oxygen, and then we'll now have a negative charge, the carbonyl oxygen, and the carbonyl group, as well as the rest of the molecule. Okay, and this molecule's name I will abbreviate as 3-phosphoglycerate, so just 3PG. And to clarify, we did just form an ATP molecule from an ADP molecule. ADP, sorry. And the enzyme that catalyzes this reaction, which is step 7 of glycolysis, is called phosphoglycerate kinase. So phosphoglycerate kinase. And recall from earlier the definition of the kinase class of enzymes are those that are transferring and moving phosphate groups around. And so we just move this phosphate group off 1,3-BPG, hence we need a kinase class of enzyme to do this. And a very interesting part of this reaction that just happened is the Gibbs free energy of formation. And this has a negative value of 18.5 kilojoules per mole. And this is interesting because if we recall the value of ATP hydrolysis, we will remember that ATP hydrolysis has a value of minus 48 kilojoules per mole. And what that means is that the reverse reaction, ADP becoming ATP, will have a value of positive 48 kilojoules per mole. So ATP hydrolysis is minus 48 kilojoules per mole. And so if we're looking at the energy contributions and why would this reaction have such a negative value of delta G, it tells us how much more stable this molecule on the right, 3-phosphoglycerate, is relative to 1,3-BPG because of this charge delocalization that can be occurring. The last thing I'll say about step 7 of glycolysis is how, because we are working with two molecules, this one ATP that we just formed now makes our total return on investment at step 7 equal to 0. So we now have received back the ATPs that we invested in our investment phase, and we got those back. And another thing to note is the importance of magnesium 2+ ions in all of this. So magnesium 2+ is stabilizing a lot of the negative intermediates that are being formed during this process. And so we can think of magnesium as like a cofactor or something that's assisting this reaction move forward. And we also see why it's so important to have all of our vitamins and minerals in a balanced, healthy and balanced diet. Okay, and so now the next thing that I will like to do is number the carbons in this 3-bisphosphoglycerate molecule. So 1, 2, 3, and so you'll note the phosphate group is on carbon number 3 right now. And so what happens in step 8 of glycolysis is the phosphate group will be moved onto carbon number 2, and the hydroxy group will be switched. So essentially what happens is these two groups will be flipped like so. So if we draw out what's happening here, what we'll find is we'll have the same exact molecule, except these two locations will now be changed. So this carbon will now be bonded to a hydroxy group, carbon 3, and carbon 2 will now have the phosphate group. And this molecule that we have just created is correctly named 2-phosphoglycerate, so 2PG. And the Gibbs free energy of this reaction, standard Gibbs free energy, is 4.4 kilojoules per mole. And therefore it's just telling us that we are going to be lying, our equilibrium does lie a bit to the left. An Mg2+ ion is also required to, or is helpful in catalyzing this reaction, and the enzyme that is involved is called phosphoglycerate mutase. And the mutase class of enzymes differ from the kinase class of enzymes. So even though we are moving a phosphate group around on this molecule, we are not moving the phosphate group onto another molecule. So if we move the phosphate group onto another molecule, it will be called a kinase. But if we are just shuffling around phosphate groups on the same molecule, the mutase class of enzymes are what perform those kinds of changes. And so if I finish drawing out this molecule that we have, putting in the two hydrogens, this will be CH2, and if I draw it like this, hopefully it'll illustrate a point that's about to happen here. What we'll see is that 2-phosphoglycerate can form a water molecule, or it can be dehydrated, and this alludes to step 8 of glycolysis, or I'm sorry, step 9. So we just finished step 8. So step 9 of glycolysis is a dehydration reaction. And in this dehydration reaction, what that means is that we lose this water molecule that I just circled in red off this molecule. And when that happens, we have to account and figure out what to do with the electron pair that's generated as a result of that. And what gets formed is something called an enol, or it looks very close to what an enol is. And so if we draw out this molecule called phosphoenol pyruvate, and it's abbreviated PEP, PEP, it will look like this. So we will have the electrons that were lost form a carbon-carbon double bond like so, and on this carbon we have this carbonyl group like we did before, and this is a CH2 molecule atom, and finally we still have that phosphate group, so OPO3 2-. And the enzyme that catalyzes this reaction is called enolase. And the standard energy, Gibbs standard energy, is equivalent to 7.5 kilojoules per mole. So this is another equilibrium relationship when we're not dealing with very large positive or large negative Gibbs free energies. And the name of the molecule that we just formed is called phosphoenol pyruvate, or PEP. And what happens to PEP is we will subject it to another kinase class of enzymes called PEP or pyruvate kinase. And what pyruvate kinase will do is it will transform PEP into pyruvate, which is the ultimate product that we wanted in order to proceed into the citric acid cycle. So pyruvate kinase is what forms pyruvate. Pyruvate kinase. And as what happened in step 6 of glycolysis, ADP will come in and do a nucleophilic attack on this phosphorus here, and we will be left with ATP as well as a more stable pyruvate molecule. And the final structure of pyruvate is a keto-enol tautomer that looks like this. So we have the same functional group we had before, and this carbon will now have a hydroxy group attached to it, and it is still sp2 hybridized. So we'll have a functional group like this. So this is the enol form of the molecule. But the enol form of the molecule is much less stable than the keto form, and the keto form, with the correctly drawn equilibrium relationship, looks more like this. So instead of this carbon being this carbon will still be sp2 hybridized, except it will now be a ketone instead, and this will simply be a methyl group. And so this oxygen has a negative charge, and so if you were to, and this as a whole is pyruvate. And so pyruvate is a keto-enol. If you were to examine the structure of pyruvate in solution, you would find most pyruvates in the keto form and few in the enol form. But as we'll see later in the citric acid cycle, pyruvate being a keto-enol tautomer is very important later on. And the Gibbs free energy of this step 10, the last step of glycolysis, is minus 31.4 kilojoules per mole. So this is a very exergonic, spontaneous process, which means it happens very readily, it's very unidirectional, and this concludes glycolysis. And another thing to note is, because we are working with two molecules, this ATP here, we're working with two of these, and we also now have two pyruvates total, and our net return on investment for ATP in all of glycolysis is now we have two net ATPs that we received back. And I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.